Do you want to show how we could implement binary search? Right, differently, using pure functions. What? What's up guys, welcome back to my channel. Today we're going to talk about binary search and how we could convert an ordinary binary search into a pure function and also apply function currying. Today, by the way, Ian is going to join and he's going to demonstrate how we can implement binary search. Also, he doesn't have any idea that I plan to implement this in the form of pure functions. So let's keep it quiet between us. He's not really a fan of function programming. Hey Ian, what's up? Would you want to show how we could implement binary search? Right. Right, a function binary search which accepts sorted array and target returns a boolean type. We have low and high as upper bound. While low lesser or equal to high, we check if the sorted array mid is equal to target. If that's the case, return true. Else, if target is greater than the sorted array mid, then we search in the upper bound. Otherwise, we search in the lower bound, return false if nothing is found. Let's run it. Let's search for 9. There you go. Works. Piece of cake. How many seconds by the way? Well, cool, Ian. That really works. And you were pretty fast. Now let's do this slightly differently using pure functions. What? And function calling. So let's refactor this and move all the variables which are rotating as function arguments. So here in this case to be low, high, move to function arguments. We can get rid of initialization code here and we can add a if statement here. If this low greater than high, just simply return or just say false. Else we can move this logic here and get rid of this piece here. And we can say here binary search. If target is greater than sorted array, then we have to search the upper bound. So sorted array, low, mid plus 1, high, and then target. So this is searching the upper bound. Else we search the lower bound. Low, high, minus 1. Right. So here I can get rid of the return statement. This can be made wow. I think yeah, this can be made wow. So now it's already looking much better. Now let's run this. Check we haven't broken anything. Length minus 1. 9. I expect true. It is true. So now we can make another improvement. In Scala, we have very good pattern matching, so I think we should make use of that. So let me here call this low and high instead, and low, high, can do a match case, low, high, if low greater than high, false, case, low, high, val, mid is equal to low plus high minus low divided by 2. So we have remove this, calculating mid, And we can check here. Can I add another match statement? Let's say sorted array mid match case mid element in case mid element if mid element is equal to target, then we return true, else case mid element if target greater than mid element. This is where we have to search the upper bound. So we can copy this piece here, say sorted array mid plus one, high target. In any other case, we can say last piece of function call, and we can actually get rid of, oh, in fact, we can also get rid of this curly braces, not needed anymore, because the whole thing just returns a boolean, so we don't need any curly braces. So also we don't need any braces here. Okay, so now we have a nicely written recursive function, and we format this a little bit, and let's log this to make sure it works. Okay, we can also add one more. We can make this tail recursive. The idea behind this tail recursive is that Scala has this internal way of converting this recursive function into iterative, uh, so that we don't unnecessarily run into some kind of a Stack Overflow problem. Now the function that we have written is already a pure function. Now there's one more step remaining. We have to apply function currying. So let's go ahead and do that. So instead of printing here, let me comment this out, and let's define or compose our function curry. So you can say here now, search function. The return type of this will be array of sorted elements except the lower bound, except the higher bound, and then accept the target, and then return the result. This is equal to, you can say here, array takes in lower bound, takes in upper bound, oh, takes in lower bound, takes in upper bound, takes in target, and then now we can call the binary search as array, low, high, and target. So this is our arrayed function. Let's apply some formatting. All right. So now let's run this function. Let's create a partially applied function, and we just invoke this here. Let's apply here sorted array, lower bound, upper bound is sorted array dot length minus 1. So yeah, we have a partially applied function. We check the type of this, we can see this return type is actually accepting an int, which is actually a target, and returns a boolean. So this accepts, write this here, accepts an int and returns boolean, just for our clarity. So now let's try and print this. Let me say here, I want to pass a line and I want to check the result. So now let's load this. True, because 9 is present in our sorted list. Now let's pass in -1. That's false. Yeah, I want to make it also a little bit more interesting now. So let's say we have integer numbers from 1 to 50. I want to check each of these elements within this range if it's available in this target or not using this partially applied function. So I can say here map each of this element, and I can say here I can create a tuple of I and partially applied function. I will pass in the result. So what this gives me is actually a tuple of this is the way we create a tuple. So tuple of int and boolean, the passed in value and the result. So now I'm gonna map this, and then for each of this tuple, I'm going to print the result. So how do we print result? It's just println element, voila, tuple 1 is if tuple dot 2, that's the result from this binary search. If this is true, then print here found, else print here not found. That's actually it. So now let's remove this and also remove this. Let's run this, see what we get. So element 1 is found, 2 is not found, 3 is found, 4 is found, 5 is missing, 9 is found as well. So now let's see exactly the result what we see here. 2 is not found, that's correct. 3 is found and 5 is not found. 6 up to 9 is found, and we don't have anything. And let's make this a bit more interesting. We add this to 100. 99 is found as well. A pure function is a function which is referentially transparent and has no side effects. If you have not watched my other video about function curry, I would definitely recommend you to take a look at this. Thank you all for watching. If you really enjoyed this video, I would really appreciate if you like and subscribe to my channel. I'll see you soon.